Students, let's talk about ionization energy. So first off, I want you guys to take a look at this chart that we have up here. And I want you guys to notice something about this chart. Let me get my little highlighter tool here. What do you notice about these highest ionization energies? What kind of elements are those? What kind of elements are helium, neon, and argon? Those are all noble gases. So as you can see with this chart, noble gases have high first ionization energies, okay? Let me change this color here so that it's easier to see on the white. So the noble gases have high first ionization energies. And I really want to point this out because I know in electronegativity, we said that noble gases don't have any electronegativity, and that is true. They don't. They have ionization energy, because ionization energy means the energy that's needed, the energy that's required to remove an electron from an atom, okay? And because they're stable and they have a stable octet, they do not want to remove an electron. So it's going to take a whole bunch of energy to remove an electron from a noble gas. And then I want you to notice over here on the graph again, what kind of elements have low first ionization energies? Which ones are these down here at the bottom that have really low ionization energies? Those are the alkali metals. The alkali metals have low ionization energies. So our alkali metals, remember, oh, I spelled that wrong. Oh, well, I can't go back. But the alkali metals are losers. All metals are losers. They have one valence electron. They have a relatively low nuclear charge compared to other elements in their period. So they're going to have a low first ionization energy, meaning it does not require a lot of energy to remove an electron from those alkali metals. And remember, when we were talking about the groups and families, we said that the alkali metals were the most reactive metals. And that was the trend for metal reactivity. It increases going to the left. These ones are the most reactive metals because they have a very low first ionization energy. It doesn't take a lot of energy to remove an electron. So higher first ionization energies tend to be those ones that are going to have to gain electrons. And they're going to form negative ions. The ones that have lower first ionization energies tend to lose their electrons easier. And so they're going to have a low first ionization energy, meaning it doesn't take a lot of energy to remove the electrons. Oops. Okay, so the trend for first ionization energy increases up and to the right. This is the same trend as electronegativity. But remember, noble gases are included. The noble gases are included in first ionization energies. So why do we see higher ionization energies in the nonmetals than we do in the metals? Remember, the nonmetals are on the right side of the periodic table. The metals are on the left side. Well, we see higher first ionization energies in the metals than we do in the nonmetals, because as we go to the right, again, we have more protons comparatively in the nucleus. And so then we have a greater attraction with those between the valence electrons and those protons in the nucleus. And then why does ionization energy increase as we go up the group? Why does it increase moving up? We have fewer energy levels. And remember, the energy levels means that we have less shielding. There's less things blocking that positive charge from the nucleus. And so we're going to have a greater attraction. This corner up here in the top right, that's our greatest attractive corner, because we have the greatest nuclear charge and we have the lowest shielding, so that we have the less distance between the nucleus. Now we can also look at ionization energies for the second and the third and the fourth ionization energy. So all of this means is that we're looking at the energy needed to remove the second or the third or the fourth ionization energies, or sorry, second, third, or fourth electrons from the atom. And so the ionization energies are always going to be increasing. As you can see here, the ionization increases from 1 to 2 to 3 to 4 and so on and so forth, because our ratio between protons and electrons is getting smaller. But you're also going to be seeing a big jump between ionization energies. So when we look at, let me change this to yellow. When we look at sodium, for example, we start with an ionization energy of 496, and then it jumps up to 4560. That's a big jump, almost 4,000. or over 4,000 kilojoules. And that's because sodium only has one valence electron. So if I'm looking at their valence electrons, once I remove that first valence electron, the second electron removed is going to be a core electron from that stable 8 valence electron inner ring. And so it takes a lot more energy to remove one of those from that stable octet. So the big jump tells us when we've stopped taking away valence electrons and we're starting to remove core electrons. So when we look at magnesium, magnesium is in group 2, and it has valence electrons, 2 valence electrons. So its first ionization energy is 738. Its second ionization energy is 1450, but the third ionization energy is 7730. So that's a big jump between ionization energy 2 and 3. And that's because we've stopped removing valence electrons and we've started removing the core electron. It always has that big jump when you start to remove a core electron. Let's look at sulfur. Sulfur has 6 valence electrons. So we would expect to see a big jump between 6 and 7, indicating we've stopped removing valence and we've started removing core. So sulfur has a first ionization energy of 1,000, and then 2250, and then 3360, and it has these gradual jumps in ionization energies. But then you get to ionization energy 6, which is 8,500. Ionization energy 7 is 27,000. That's a huge jump. So look for the biggest jump. Everything before the biggest jump is valence. Everything after that big jump is a core electron. Okay, let's see how this works. So we're looking at this table down here. We're trying to figure out some information about element X. Okay, so these are first, second, third, fourth, fifth, sixth ionization energies of element X. So when you're given these successive ionization energies, you're looking for that big jump, the biggest jump. And so here, that big jump is happening between the second and the third ionization energies. So we're going from 1450 to 7732. That means that everything from here over, the first and the second electrons, those were valence. Those were our valence electrons. But everything to this side, everything over here on this side of things, that means that those were core electrons or inner electrons. Okay, so this means that it had 2 valence electrons. So if we're looking to see which group this was in, we would say that this was in group 2 because there was 2 valence electrons. And we can see that that big jump between second and third ionization energies. And then what would the charge be on element X? So this goes back to those common ion charges we put on there on the periodic tables during the first or second video for this unit. And so that charge for group 2 is always going to form a +2 because they have 2 valence electrons. They're the alkaline earth metals, which means that they're going to lose those electrons. And so they would form a +2 charge. Okay, so that's all you're going to have to do with ionization energies. If you have a question, just let me know. All right, bye.